Turns out that the queue can also be implemented using a linked list in addition to the array. And so we should talk about how that can work and then show code for doing it. So what does it look like? So this was our diagram for a stack. I copied some nodes so that we have basically a singly linked list here just as a normal list with a head. Of course, while the stack really only has one location that matters, the top, because things are added at the top and they are removed at the top, the queue isn't quite the same. Turns out that for the queue, we have both, instead of calling them head and tail, I will briefly write this out as tail. The queue, you might think of it as being a front and a back. Okay, there's the front of the line and the back of the line. The back of the line is where we enter the queue, and the front of the line is where we exit the queue. And the question is, which one of those is head and which one of those is tail? Does it matter? Could I do either way? Okay, and so in order to answer that, we kind of have to think about this. What do we do at each one? So at the front of the line, you remove, and at the back of the line, you add. Well, we've seen here that the top, the head of a singly linked list, can very efficiently both add and remove. So head could be either the front or the back of our queue. What about the tail? Well, it turns out I can efficiently add at the tail. I could make a new node here, I could link it in, and I could point the tail to it. Okay, we did that with our append on our singly linked list buffer. But you cannot efficiently remove from the tail on a singly linked list. Imagine that instead of having 2 elements here, this had 200 elements. So head and tail were very, very far apart from each other. Because these links are one way, knowing about the tail, I actually still can't remove it, because in order to remove the last element, I have to know about the second to the last element. So the tail is a good place to add, but it's not a good place to remove. And that means that the tail really needs to be the back of our queue, where we're going to add elements, which leaves the head, by the pigeonhole principle, to be the front. Okay, so then what do the operations look like? Well, when we enqueue by making a new node. I'll go again and give it the value 3. And we link it in. So I'm going to link from what is currently the back and point it to that new node. And then that becomes the back. Okay. There is one special case here where if the collection had been empty, we're going to need to handle that differently, because then both the front and the back would point to the same thing. If it's not empty, all we do is we change back, we don't modify front. What about dequeue? Well, dequeue is just like popping off of a stack. It takes the link from the front and changes it over to the next element and allows the garbage collector to come pick up this node. So that's the way that our queue is going to work. Let's go into the code and let's actually write one. So I want up here to make a new class that I will call list queue, and I want to give it the methods of our queue abstract type that we made previously. I also need to make it have a type parameter and say that it extends queue of that type. And we want our version of the queue here. We just showed in the diagram I can do this with a singly linked list, and once again, if I can do something with a singly linked list, if I don't need the power of a doubly linked list, I am going to make it a singly linked list. It turns out that in this case, I can't use a case class. I can make the data immutable, so my data can be a val, but next can't, because the operation of adding an element here, when we added the 3 on, we actually changed the next pointer of this node. So the next pointer is going to be mutated by the enqueue operation. So I actually have to make that a var. We're going to have private vars for the front, which is a node that starts off as null, and a private var for the back, which is a node that also starts off as null. So, is empty. When is our queue empty? Well, our queue is empty if it doesn't have anything on it, which would be potentially something like the front is null. You could check for the back is null. Turns out that's a slightly different check, and depending upon exactly some of the things we do in enqueue and dequeue, we need to come back and make sure that what we're doing here is going to work. Peek is really easy. Peek is just going to give back the data at the front. Okay. Dequeue. Dequeue needs to pull off the element from the front and give it back to us. So let's go ahead and let's start by remembering the data at the front, and then we're going to give that back. But then we have to change front. We have to make front equal to front dot next. And that would be sufficient for the case that we showed here. But what if I just pulled off the last element? If I just did a dequeue and I only had one thing on my queue? Well, in that case, front will wind up being set to null. It might also be nice to set back to null, just to make sure that everything is consistent. So if front is null, then back will be set to null as well. Okay. Up last is enqueue. When we add elements onto our queue, they're going to wind up happening at the back. And the normal code, what we went through kind of in our figure here, was I make a new node that stores the data. I have the back's next point to it, and then I change back. So we can write that up. I can say back's next, and remember this is why we made next a var, is equal to a new node that stores A and doesn't point to anything. And then I set back equal to back's next. And that all seems great and happy. And it is, assuming that the queue wasn't empty. Because if the queue was empty, then back would be null, and null.next is a null pointer exception. Okay, so we can only do this in the case where it's not empty. So I'm going to say if is empty, then I want to do something else. Otherwise, I'll do the code that we just wrote. What do I need to do if it's empty? Well, if it's empty, I'm still making one new node. Well, that new node is going to be both the front and the back. So I'm going to go ahead and set the front equal to my new node that stores A and null. And then I'll just set back equal to front. That way both of my references will point to the same node here that I've just created. As long as it's not empty, I can do this procedure here. So there is a list queue. Once again, we're highlighting the fact that the queue is abstract. It does not care if it's implemented using a singly linked list or if it's implemented using array. Both of our implementations are technically order one for all the methods in them. So they meet our general requirements for this ADT. And if you want to know exactly which one is faster, you would have to do real performance testing on them. I have not run unit tests here on either one of these. But we already have unit tests for the stack queue. We have a test array stack and a test array queue. You can actually copy this code. And what do we have to change if we wanted to test to get either the list-based version of the stack or queue? All we'd have to change is that one line right there and then the associated import. So instead of running this with an array stack, I would run it with a list stack. Because the interface is the same, everything else should work exactly the same way. So it isn't hard for us to create a test for this, given the fact that we've already tested our other stack and our other queue.